and then divide by 2 because that's a factor of safety. So now we get the number for the strength of the well per 1 centimeter of thickness and per 1 centimeter of the length. So if you want to have the force, you multiply this with the size of the well in centimeter and then multiply with the length. You have the force. This is for E60. You can use the number right away. And this is for E70. You can use the number right away. For me, I cannot memorize this, so I just calculate it right away. Because it's very easy to memorize in terms of the understanding. Right? And this is LIFD, so we change the factor of safety 2 into 0.75 instead, and you have the numbers. Okay? Another important issue that we should be able to finish, say, before the break, is the issue with the base metal. Because you can weld as thick as you want, but if the two pieces of the metal that you are going to weld together are not strong enough or less or weaker than the weld itself, how can the weld carry the force as much as it could when the base metal is going to fail before the weld? Right? Let's say if your base metal can carry the force up to 10 tons before it fails, and you weld so that your weld can carry 20 tons. What's going to fail? It's the base metal, right? So your welding can never be stronger than the base metal. In other words, you don't have to create the weld that is way stronger than the base metal. It's no use. Do we agree here? Of course, right? So if you have a very small plate and you create like, wow, that big of the weld, it's nuts, silly. So we need to check the strength of the base metal. And again, they suggest that we check both yielding and rupture. But again, how can rupture occur before yielding? So I always check with yielding. Okay? And this is the strength of the base metal underneath the weld. We can always say that, you can multiply the area of the plate underneath the weld and then multiply by 0.6 Fy. But generally, the length of the metal underneath the weld and the length of the weld itself should be equal, right? So that means we can just, compare the strength per length of the weld and the base metal. That means, wrong button. If I'm going to draw another picture, say that's my weld. Looks like a loaf of bread. And then that would be the thickness of the plate underneath. They should share the same length. So we can just compare the strength per 1 unit length of the weld and the plate. So the strength of the weld would be, say, what's the number previously? Let's say I use E60 ASD. It becomes 0.891D. Then I can just compare this with, 0.6 Fy and then the thickness of the plate. Right? So you can easily obtain how much size of the weld that you should use before the weld becomes stronger than the plate. If the weld becomes stronger than the plate, you would know that it doesn't matter how much you increase the size of the weld, it doesn't help because it's going to fail here. Any question, ladies and gentlemen? We still have like 5 minutes. So let me, okay, some just to enjoy drawing. Yes, sir. Oh, that's another beast. If you talk about the 2.3 millimeter or 3.2 millimeter, that's a cold form steel structure. And I think they perhaps have a different specification for welding. Right. My apologies. I don't remember, but yeah, it's a different kind of a steel. It's called cold form steel structure. And they have the way to weld it, but it may use a different approach from this because it's so thin, yes. I think you can also, I don't know if it's free for downloading, but now I can say that EIT, Engineering Institute of Thailand, have the cold form standard, which is very, very up to date. You can try to obtain that as well. It was done by someone I know, and he's pretty good. I think it's Dr. Nataporn, no? Right. So it's a very long because he's also the Air Force member. Yeah, very long title in front of his name. Assistant Professor, Colonel something. I don't know. It's a really long name, but yeah, I think he's done a good job on that one, and you can check on that. Okay. Oh, right. That button. Sorry, lost myself a little bit. Here, the last one is this. Another issue with the well is that the strength of the well depends on the direction of the force acting on it. Our general, say, formula that I just mentioned is based on the fact that the force is acting parallel with the well. So if the angle between the force and the well increases, the well will be able to take more force, as this formula suggests. And if you look at the formula, it will give you the maximum value when the angle here becomes 90 degrees. When it becomes 90 degrees, the sine term will become 1. So that means this term becomes 1.5. So yes, ladies and gentlemen, if you have the case where, gotta come back here again. If you have the case where you have a plate like this, you have a force like that, and you have the wells here, this well is 1.5 times stronger than this. And believe you me, they use it. And I use it too. But it's going to be, the deformation is going to be a little bit less. But it's stronger, yes. This work was done by the great Professor Kulak. The stress-strain, the load deformation relationship in the bows was also done by him. So one very, very distinguished professor. And he's Canadian. All right, Tam. As usual, the first session is over, and we have like 60 slides left. I thought we were going quickly, and then again, it happened again. 10 to 15, that's fine. It should not affect the outcome that much. It's like 60 slides. Okay, so back to the business about the force now, because we already know the strength of the well itself, right? So, okay. Here, because the well is some sort of a continuous material, so to calculate the stress just like the way we handle the bolts would be difficult. So the way we would handle the well just to convert everything into the stress. and trying to find the maximum stress and combine them. And we have all kinds of stress depending on the force that we have. We have a shear stress. Oops, forget that. Okay. We have the shear stress, and that means the force divided by the area. So we have the shear stress. We have the axial stress, the force divided by area again. We have the flexural stress, that's my over I formula, and we have the torsional stress. The formula is pretty much the same as we saw from the boat thing. And then after you calculate all the stress, you can just combine them together by, again, using the vector sum. You know? Sum everything in its own direction and then sum them up by using the vector. It's like that. And yeah, we have the issue with the eccentricity, just like with the boats. And again, we have the classical method, and we have the ultimate strength method based on the instantaneous center of rotation, just like we saw before. This is a simple example of how we can approach this with the classical method is this. Again, because when we have the stress, and if the stress is normal, we don't have to do anything, right? We can just combine them. But when we start to have something like torsion, that means we should know that the maximum stress should be at one of the corners, because the torsional stress formula would suggest that the farther you are away from the centroid, the more stress you should have due to this rho term. The bigger the rho or the bigger the L here, the more the stress. So when we have a situation like this, it is our job to investigate each corner and see which corner will give us the maximum stress. That would be the corner that every stress go into the same direction, so to speak. Okay, and the calculation of the stress, the torsional stress, is again depend on that torsional stress formula. And I don't know why I use IP with the boats, right? But for the wells I use JW. It's the same thing. Maybe I got bored. I don't know, but it's the same thing. And again, when you calculate the moment of inertia for this, it becomes just the a typical formula, but this time you may want to include the BH cube over 12 for this piece, maybe in the x direction, and you may want to include the BH cube over 12 for this and this in the y-axis, and then we have the AD square term, just like the boats. Okay, and again, when you have the stress coming from torsion, it's always perpendicular to the moment arm or the torsional arm, and we need to convert that into the x and y component by multiplying this with the sine and cosine function. And then again, the d will be cancelled out, and you are left with the x component is the force multiplied by the y distance to create torsion, right? And the force in the y component will be multiplied by the x distance to create a torsion. It's pretty much the same here. And it's also pretty much the same with the instantaneous center of rotation, in that we need to try to find a way to locate the instantaneous center itself. And you need to have a day or so to do it, things like that. And if you have the manual, you can take the results from one of the tables available in the manual right away. Okay. Again, we have the bolts now, we have the welds now. It's time to go into the third one, that is the member itself, when it has the effects from holes and so on. But we already visited this yesterday, so I can go quickly, I suppose. When we have holes, you will have to check the yielding of the member itself again, which you can argue, oh, I already designed it. But it's not a bad idea to just check to make sure that, okay, your member will survive the force again. And yielding itself is the base that you can compare the result from other limit states to say how well your connection is designed. Because when you design a connection, the maximum force that your connection can transfer shall never be greater than the yielding of the cross section, right? That's the maximum your member can carry, which also means if you can give details of the connection and the connection can transfer the force very close to yielding of the member, that means you have done a good job. Okay? Let's say 90% efficiency is a very, very good number. Anyway, the next one is the tensile rupture in net section, which we already mentioned yesterday. So I can just go quickly, right? This is the same as yesterday. If the direction of the force is changed from tension into shear, instead of having the tensile yielding, you have shear yielding instead. So instead of having Fy multiplied by the gross tensile area, you now have 0.6 Fy, that's a von Mies, then multiply by the gross shear area. So in this case, that becomes the shear area, right? And wow, this is from the history that I told you yesterday. The phi is 1, the factor of safety is 1.5 for shear yielding. For shear rupture, it's pretty much the same as tension, but you have the shear stress instead. One major difference is that when you have the shear rupture, even though it is named shear rupture, there is no shear lag. It's kind of funny, isn't it? It doesn't lack shear, so you already have shear, right? So no shear lag, okay? And the factor of safety and the phi are the same. And next is the block shear, same as yesterday. Okay, that is a combination between tension and shear failure, and you need to check tension here, and you need to check the minimum value from shear rupture or yielding. The next one is the bearing tau that we already talked about yesterday as well, but I forgot to mention because yesterday we got two formulas, right? Oh, that's still block shear. So where's the, I must have erased it. My apologies, but this should be the block shear, but then I forgot to do the bearing tau out. So please refer back to the stuff that we had yesterday. My mistake. Need to fix this. Because this is a picture of the bearing tau, but the content itself is block shear. But luckily, we already mentioned about that yesterday. So let me go back to the slide yesterday a little bit. Oh, how can we do it? There, right? Here, right. Well, there are three sets of formulas yesterday, but generally we would use the top one because this is the formula that you can use and you can be sure that the deformation will not be excessive. If you don't care about deformation, you can use the larger capacity here, but that means when the force is that much, the deformation of the blowhole will also be large. And generally, I have never seen anyone use this before. Okay? And one more thing. The bearing tear out is, very, very hard to occur, just like block shear. Because look at the number itself. It's only 2.4 FU, right? And here's 1.2 FU. So bearing tear out has a small chance to occur. It can occur, yes. It can occur when, again, you have small connection, like maybe 2 bolts. So you have 2 bolt holes, so that can occur. Or when you have a very thin connection. For example, the most critical one is always the beam web or the web of the edge. Because we all know that the web is generally very, very thin. And when you connect there and you have the bolt holes, it can, fail quicker than other limit states or failure mode. It can. All right. Um, ooh, difficult to use. Huh? How do I do it? Okay. Technical glitch. All right. ครับอุ้ยอ๋อมันยังไม่ได้เปิดครับไม่เป็นไรครับไม่เป็นไรครับเปลี่ยนไอตัวไฟล์พอดีครับโอเค we back live นะ so now we know the basics we know the bolts we know the welds and we know the how our member can be affected when we do the connection so it's time to get into the types of the connection now and we have like approximately 1 hour before lunch so let's see how far we can go first of course is the connection that transfer tensile force or tension so we have the direct load it looks like that we have the hanger connection which I already mentioned that if the plate is too thin you may have the problem with the prying force and then the bracing if it is the compression you can have the here the column base plate and you know I did not include the design of column base plate in the presentation I never did I think it's too simple maybe is it if it's a common force it should be simple but anyway we can have beam bearing and column base plate and column splice which in general when you splice the column well we don't have to worry about the force actually right because if you finish to bear it means that the force is transferred directly from member to member but then again if you want to design for it you can convert compression into tension and maybe just use it 50% to design for the connection or imagine that you have the eccentric load and design the connection to try to withstand that but the eccentric load should be just a very small amount of the load okay I don't know if I have the number with me. Maybe I should in the next few slides. And then you can have the shear connection, and presented today with us, it's going to be the typical type of shear connection that we that are generally used by engineers. Right? It doesn't mean that you cannot create something, you know, away from this. It depends on the situation that you may have. Okay. This is the shear end plate. That means the plate is at the end of the beam. And notice that the plate here is only between the web region. And it carries only shear. That's why they call it shear end plate. And when you use two angles, it is called double angle connection. When you use only one angle, it is called single angle. You can have this as a single plate, one plate. So they call it single plate. Or shear tap or fin plate. It's the same here. One plate with the bolts and then the welds at the end. Or the T or a seat like this. A seat like this is called the seated connection. Okay? These you know, generally are in the region of the beam web because it is a shear connection. And the beam web is the element that say predominantly carries the shear for the member. Okay? If you want to transfer the moment, that is the moment connection, you're going to have to find a way to connect the web. I'm sorry, the flange. So you can see in this detail, these two flanges are welded to the support, so it becomes the moment connection. Because right now the force in the flanges, which come from moment, can now be transferred through the welds here. Or we can use an extra plate and then bolt them together like this. So this is called the flange plate bolted. Or you can weld this flange with the plate. It is called flange plate welded. Okay? And then another kinds of moment connections, you know. We can have something like this that is called the T-stop. You can add more seat to this. But these things are, say, they are called semi-rigid moment connection, which, well, It's going to be quite something to handle. And it is a special requirement that maybe Ajahn Sutat can tell you because it's the earthquake stuff. Okay, but generally, if it's a typical connection, you either have the shear connection or moment connection. We don't need the semi-rigid detail like this. The semi-rigid would mean that it can carry moment, but it will have rotation. It's something in between, between the pin and the fixed support. And this is another one. See, this is also the end plate, but this end plate covers both flanges. So this is no longer a shear end plate, it becomes a moment end plate that is capable of transferring moment from the beam into the column. Okay? So now, to sum it up, we have the connection that is used to transfer the axial force. If it is the tension, we already see that you need to consider the big four that will go to the Champions League. That will be the yielding, rupture, block shear, and bearing tower for members with bolt holes. Okay? And then when you have either the bolts or the wells, you need to consider the rupture failure of those stuff themselves. Bolt shear rupture, bolt tensile rupture, if any, and weld shear rupture. And you may have to consider something extra depending on the types of connection that you have. For example, the staggering effect, that is when you have the zigzag pattern for the bolts, like this. I don't know why I never have the slide for this stuff, and then I always end up having to write something like all the time, draw something. So when the staggering effect is something like, okay, when you have the bolts like this, the failure that may occur, maybe it's rupture in this line or rupture in this line. The green line has more bolt holes, so the net area is less than the pink line, right? But in the green line, you will have the help from the staggering effect. So the A net for the green line would be equal to, say, the total area minus the 3 bolt diameter, but it's plus that, so I'm going to use a prime here so that you know it's not really a bolt diameter, right? Multiply by the plate thickness, then plus the staggering effect of these two, which comes from, this is S, this is G, S square over 4G. And then multiply by TP. Okay? And you have two of them, so multiply this by 2 as well. That's the staggering effect. So the green line may not be the most critical path for the rupture to occur. You have to compare the net area between the green line, which has 3 bolts, but the staggering effect, and the pink line, which has just 2 bolts. Okay, so that's staggering effect. Another issue is the Whitmore section. For the Whitmore section, it generally with the gusset plate, because when you have a gusset plate, the plate itself can be so big, and your bolt holes may be here. So when you apply, say, tension comes from the members that will be connected here. Does it mean that your gusset is going to fail here, this zone? No. Some guy, I think his name must have been Whitmore, right? He said that the failure, the critical section should be here. And this is 30 degrees. Okay, and this becomes known as Whitmore section. So you just project 30-degree angle onto the end of the connection, and there you have Whitmore section. And consider the yielding over there. Okay, this is examples of some of the things that we may need to consider. In addition to the basic failure modes that we have. Okay, and we're not done yet. All right. Okay, so I have it here, a compression. If it is compression, you may need to design it just in case that, you know, if you have the not so perfect finish to bear, maybe it's called the kink effect. That's when you finish and you know the cross section of the two members are not truly square, so it just can wobble a little bit at that connection. So you may want to design a connection that can either carry the force but in tension up to 50% of the compression that you have in the column. You take the compression force, reduce by 50%, and design your connection as if the force was tension. Or think that you have the force in the, I think in the lateral direction, but only 2%, and apply that force as lateral force on the connection, and design the force design the connection to be able to take that force. They have the second one because the first one, it's too big. Okay, and that's it. Now, this is the same picture as yesterday. To sum it up, when you have the axial force member, that you follow the load path, and you know that yielding can occur anywhere, and then the rupture, block shear, and bearing down, and then bolt shear rupture, and so on. Well, we follow the force, and then check all the failure modes and the limit states along the way, and then that's it. Now that's it for the typical axial force connections, which if we used to have some lessons from the undergrad level in the university, I think it's up to here, right? So now we're gonna go into the next level by start talking about the shear connection. Now, as we all know, a shear connection should be for simple beam, right? Because we need only to transfer the shear at the end of the beam. But a simple beam, on paper, we have the roller and a hinge. But in the real world, if we can go back to these pictures, and these are the typical shear connections that we use. It has dimension, right? If you draw a support on paper, it's just a dot. But this is not a dot. So the business of taking care of the shear connection is just to figure out where the pin is on the connection. Because the pin is not a dot, and you see the connection has dimensions. So we need to have the assumption about the location of the pin, and if some components are at the location of the pin, we can say that those components are free of eccentricity problem. If it's not, when we design this, we need to consider the effect of eccentricity that may affect the strength of our components. Okay, so that's the basic idea. Where the pin is. So let's go into details right away. You may want to flip back and forth between the picture, because if you can recall the picture of the end plate itself, you want to go back to the picture? That's okay. The end plate itself, the dimension of the connection is just the thickness of the plate. So we can safely say for the shear end plate detail, we don't need to consider eccentricity at all. That means when you want to estimate the strength of this connection, it's just based on, you know, the strength of the plate, the strength of the weld that connects the beam and the plate together, and then the strength of the bolt, and that's it. Very simple to calculate. It's a dream come true connection, right? But wait a minute. Our lives cannot be that beautiful, can it? Maybe something in a corner, around the corner, sorry. Okay, so that's it. For double angle, because we are considering the shear connection, so whenever you use the bolts, we can consider that's where the pin is. Because when you have the bolt, the beam can easily rotate where the bolt is. But when you weld your angle together with the beam or with the support, that part will become difficult to rotate. So whenever you use the weld, eccentricity must be considered. So that means if we have, like this picture, double angle with bolts everywhere, we call it bolted double angle connection, no eccentricity, very, very easy to calculate. Actually, we can say the pin is right there at the surface of that beam web. So the bolt on that side has no eccentricity, and if the pin is right here, the bolts in the middle also has no eccentricity.